Okay, before I start, I want to put things in context. Technology in the past 5 years, 10 years, whatever, has moved towards giving people what they expect, what they ultimately want, not necessarily what they capture of the real world. So, for example, we all understand, and I understand, when I use my phone, I'm going to get a photo that looks like what I probably want it to look like, and I often do want it to look like. The sky will be bluer. People's faces will be a little bit brighter, right? The colors will be cleaned up. But I know that's not what the camera is seeing. If I look at the raw files from the camera, they're different and they aren't as good as my larger sensor cameras that I have. So if I want to do real photography, I don't know what to call it, then I'm going to use a real camera, right? But if I want to get a good photo of me and my family, then this is great. And this technology has moved to devices like audio recorders, like the Zoom F3. If I want to record somebody and get an audio file to hear them as is pleasing to hear them, this will give it to me, just like my phone. And it has its place, and it's fine. Many times, that's what I want. I want to just give me what everybody will like, what I will like for these circumstances. Give that to me, and this gives that to me. But if I want like a real camera, if I want to record in as perfect fidelity as I can what the camera saw or the audio recorder heard, something like this, and I'm going to use something like this. Again, they serve different needs. So what I'm going to go through is not about what's better or worse. It's just explaining the differences. And I'm going to explain why this does things that degrades what it captures in a way that isn't good if you want to really do real audio work with it. Just say the same thing where I could analyze the images in this phone and show you that they aren't true fidelity of what the camera saw. They're what we want to see. So I just want you to keep all that in mind as I go through this. So this is the setup I used. I took two pencil microphones of the same type, and I aimed them into a speaker, and I played a test file. And the test file went to the Zoom, and it went to the Tascam. And I also switched the microphones between them to make sure we're not seeing two different things because of the microphone. And then I embedded in these spectrograms these images. And the images will allow us to sort of see how each device is handling different amplitudes and how it's handling different frequencies and how it's sort of dealing with both at the same time in a way that we can visually see the differences between these devices. Okay, this is the test file. Now I used Python to create this. And as you can see, this is completely idealized, right? So I mean, these are the amplitude tests. So basically, this is a tone, so this would be like 400 hertz. This is 1 kilohertz, something like that, right? So each different kilohertz rising in amplitude, and this is basically just the frequencies only at the same amplitude. And this is a word I'm going to embed so you can see it in the spectrogram. So we're going to do that right now. Let's go look at this in the spectrogram, and there you can see it. These are each of the tones. Well, each tone goes up in amplitude. So think of the line as starting at a low amplitude and going up, going down, going up, down, going up. It's going like that. And then this is basically just a frequency going from top to bottom. And then I've embedded the word test. Okay, does that all make sense? Hope so. So let's look at the first set. Now, I switched the microphones. So this is basically the Zoom with probably the left microphone, the Zoom with the right microphone, and then the Tascam with the left microphone, and then the right microphone, right? So just so we can see that there isn't a difference. Now the first difference I saw, well, let me just show the spectrogram of the Tascam too while we're here. Okay. The first thing I noticed is that there's a difference in microphones on the Zoom F3, which I don't understand why there is, because on the Tascam they look pretty much the same. So something weird going on there, I don't know. Anyway, I just thought I'd point it out. So the reason we see black here is it's an idealized wave file. It's created from from data that's going to play this. But when it plays through the speakers, all bets are off, right? So when the speaker gets a tone like this, it's going to create harmonics, right? And that's what these other little lines are. Now, you'll notice, especially in this one, that there isn't a lot of harmonics, that there isn't a lot of data right here. So you can just see, all this black space here, right? That's all, just like this. So the first conclusion you might come to is that, yeah, wow, the zoom is really good because it didn't show, the spectrogram. It didn't record stuff that wasn't in the file that we played. But that isn't a correct way of looking at it. Remember, the speakers are going to play these tones, and then they're going to create harmonics and noise and all other kinds of things. So we know as a fact that the Tascam, which has no noise reduction or anything like that, it's just, and I have this basically on 32 dB in the high gain setting. You know from my other videos that this is basically the lowest gain. So 32 dB, high gain, right? And so everything it's picking up here is real. But you might make the argument, well, how do you know, Max? I mean, how do you know it's real, right? I mean, how do you know that the zoom just is not picking up, these audio samples because they just aren't there? Well, we know because of the harmonics. So all speakers will generate harmonics from a tone, and that's what all these lines are going up evenly. So if you look at, let's just say this line, right? Each of these dots is a harmonic, right? It's the first harmonic, second, third, fourth, fifth, sixth, seventh, eighth, and they all get closer, right? But look at the harmonics in the zoom. The first, second is right, third, barely gets the other one, gets this one, and really gets none of them up here, see? See all these little harmonics here? And there are none in the zoom. These harmonics happened. Again, they shouldn't have happened because they're not in the wave file that we're playing, but they do happen because that's the nature of speakers, right? That's the nature of the real world. That's what I heard. And again, I'm using the speakers so I can replicate the experiment, but what this is saying is if you're listening to somebody singing, the zoom is not going to record all the harmonics. It's only going to record the main harmonics because it's doing a lot of on-the-fly noise reduction, which really isn't noise reduction, it's sample reduction. It's removing samples that it believes are not part of the main part of the signal. It's basically looking and saying, okay, well, if I have a sample here, I'm going to keep it. Oh, but if I have a sample here, I don't think that's right? Because I'm looking at this and I don't think that's right, so I'm not going to record it. But it was there. It was there in the environment, and it was there in a recorder that's picking up everything. So that's how we know that the Tascam is picking up information, again, all these harmonics that we know are true in reality and are not true here because they're not random. They have specific places, right? So if we look over here, right, we know these are specific harmonics because they have very specific places. So I'm looking at these right here. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9 distinct harmonics. Here we have the 1, 2, 3, 4, 5, 6, 7. There are only 7 distinct harmonics in the zoom, and there are 9 distinct harmonics in the Tascam. Again, those harmonics are there. The other way we can see these differences is if you look at, I've expanded this a bit. Actually, let me just make this all equal. So if you look at the word, here's our word that we want to see perfectly. And here is from the Tascam. The Tascam, through both microphones, looks much closer to the word embedded in our spectrogram, which is embedded using both frequency and amplitude tricks, so to speak. And if we look at the zoom, it isn't as good. In fact, it's horrible in this one. Again, I don't know why, but for whatever reason, the zoom went ape on removing samples it didn't like. In this one, it really cleaned out the signal. In this one, it didn't. But even in this one, it's worse than that. So, bottom line, again, the zoom delivers me audio that sounds good to me that I want to hear. But if I look at it closely, it, just like my phone, it doctored up what it recorded. I'd also sort of say like the zoom is sort of like, the camera has a really small sensor, and that's one of its problems. The zoom doesn't have a small sensor, but it's like a small sensor because the preamp is operating so low to the microphone. So it basically takes any microphone that in this thing, right? A microphone in the Tascam would be like a large sensor microphone, but the zoom makes it a small sensor microphone because of what the ADC does. So anyway, I hope you find this helpful, and feel free to ask me any questions. I know, this is a very crude test, and there are a million ways I can improve it, and I'm not an expert here, but I hope it just shows you that, again, as I've always said, there's no free lunch, okay? The Zoom is a nice little device, but, if you want, it doesn't get away from the laws of physics. And the laws of physics, this is a Tascam. This is the reality of what was played, and it captured the reality by recording that.